I hope you had a good break. Let's get back to the model and to basically go to the actual contents of the model. So we're going to look at model which is called also integral. It's called the fixed investment model. And basically what we want to do is we want to provide a model which is as simple as possible in order to highlight the effects of moral hazard in this case, so hidden action that we want to study the consequences of. So let's look at a very simple model which does actually capture that. So we are going to have a look at an entrepreneur, and this entrepreneur is going to carry out a project which is going to be risky and which involves outside financing. So that means this entrepreneur needs to make some investment, and he's going to involve some outside investor to actually attract the money. And now the question is going to be, there will be some outcome of this project, so it will pay off or perhaps it will not pay off in some states of the world. And the investor and the entrepreneur have to agree on how to split the returns of this project. So let's have a look at such a model. So what we do want to do is to make this interesting is to add agency costs, or in other words, to add moral hazard or hidden action, as we mentioned before. So what the entrepreneur may do is he or she may mismanage the project. So what does it mean? Well, for instance, taking a private benefit which lowers the probability of project success. So there is some attraction here for the entrepreneur to do something which the investor cannot observe, but which gives some benefits to the entrepreneur. So you might imagine some of the money is actually not going to the project that the entrepreneur promised it to go to, but actually it will be siphoned off to be invested in some side project, which might be a pet project. Or perhaps actually there is something non-monetary, like the entrepreneur likes to work not as hard for this project as might be best in order to sort of provide the desired outcome for the project. So what would the model look like? Well, there's this project, and to make this distinction between uncertain outcomes, risky outcomes as clean as possible, it just can have two outcomes. Either the outcome is going to be some positive number R, so we keep this completely general, just some positive number, we call it R. So it might be 100 euros, it might be 1,000,000 euros, we call it R. And with some probability, the project will fail, and then there will be no outcome, zero. And of course, what's going to be crucial is there's some upfront investment, and that upfront investment is called I. So we have to get used to denoting the variables in this model by letters, so to keep things as general as possible. So you won't see us often sort of write like numbers like $100 or whatever. Get used to letters. That's what we need to do when we study theory. The entrepreneur might have some money of him or herself, so we call those his or her assets, A. Of course, this A is going to be less than what's actually completely needed to finance the investment, otherwise the entrepreneur wouldn't need the investor, so A is smaller than I. That's what our assumption is going to be. So that means that the investor is going to be called upon to provide this remaining I minus A. That's going to be the investment that the investor is going to make in the entrepreneur's project. Okay? So as we said, this project is going to be risky. So if it succeeds, it produces some outcome R, and that's going to happen with some probability P. So P is some number between 0 and 1. It's a probability. So again, what's going to be crucial is this agency problem. So this P is going to depend on some unobservable effort, so unobservable at least to the investor, the unobservable effort that the entrepreneur is going to be putting into this project. So, and to keep life as simple as possible and as easy to analyze for us as possible, there's just two courses of action for the entrepreneur. So either the entrepreneur is going to put in the desired effort, the high effort, and then the probability of success is high, and we call it PH, and this H of course stands for high effort. So that's a large probability of success. On the other hand, the entrepreneur might also say, oh, I'm not going to provide effort, or I'm going to siphon off some of the money to spend it on something I like more, a nice room or a pet project. Well, in case of this no effort alternative, the probability of success is going to be low, so we call it PL, the lower probability. And the attraction for the entrepreneur is, well, if the entrepreneur decides to spend no effort or low effort, then there will be some private benefit, and we call that B. So there's a difference between high and low effort, PH and PL, and probability of success. And PH minus PL is, we will denote that by delta P, the difference in the probabilities. So now if the entrepreneur then exerts efforts and the payoff is going to be positive, or rather the net present value, which is what you see here, is going to be positive. So what does that mean? Well, the probability of success, which is PH, if this entrepreneur exerts effort, times the outcome if there is success, which was R. So that's the expected outcome of the model, of the project, PH times R, minus the cost of investing, I. That's going to be bigger than 0. So this is going to be a positive NPV investment. And we already decided, I looked at this before the break. In a perfect capital market, such a project which has a positive NPV should always receive funding, right? Now, the risk here is that the entrepreneur might not exert effort. And in that case, the payoff, or the NPV of this total project, is going to be negative. So the expected returns of this project, PL times R, expected outcome of this project, PL times R, minus the investment, I. And even if we add to that the value of the private benefits that the entrepreneur gets when not exerting effort, that's going to be assumed to be negative. So what does that mean? If there is no effort, it would be a welfare loss to finance this project. The project should not receive funds in case of no effort. So we want a project, if we want to finance a project, we should try to make sure that this entrepreneur is going to put in the effort. So let's summarize this in a diagram. So we start at left-hand side with the investment I. So there's going to be some investment I that will be financed by both the entrepreneur and the outside investors. Then the entrepreneur chooses his action. The action is going to be either putting in the effort, that's the upward branch, or not putting in the effort, the lower branch. And in that case, the entrepreneur gets these private benefits, gets to be lazy, or gets to get his pet project on the side. And then if you go further, after spending the effort, there is a choice by nature, you might say. The dice are thrown. And with probability PH in this effort branch of this project, there's going to be success, and we get R. And with probability 1 minus PH is going to be failure, and we get 0. And similarly, if there was no effort, so a low effort, then still we might be lucky, and there is still some probability of success, but it's just lower. It's called PL. So with probability PL, the lower probability, there still is success, even in spite of this low or no effort, and we get R. But 1 minus PL, of course, is now a bit bigger, and 1 minus PL is now the probability of failure. So have a look at this diagram and see if you understand this. And if you wish, you can actually stop the slide here, or the video here for a bit, and wonder, do I understand what's going on here? So let's go further then. Let's look at the funding contract. So we argued that this funder, this investor, is needed to supply this additional shortcome I minus A, because the entrepreneur, him or herself, has some money, its assets, which it puts into the project, but it's just not sufficient. Now, in case of project success, so when this R is realized, we are lucky, nature chooses success. There is an amount of money, R, and that needs to be split between the two players here, right? So there's one player who is called the investor, there's the other player who was the entrepreneur, and they have to decide ex ante, so when making the investment, when agreeing about providing this funding, they will have to make some agreement, and we call this a contract, on how to split that money R. And we'll denote this split into, well, one part, let's call it RL for lender, will go to the lender, who's the investor. And the other part, or another part, RB for borrower, will go to the entrepreneur. And naturally, of course, the sum of these RL, the lender's part, and the borrower's part, RB, that's going to be the total amount of money that's available when there is success. So R equals RL plus RB. So that's the funding contract, just deciding what is RL and how high is RB. How do we do this split if we have success? So in case of failure, of course, there's no payoff from the project itself. It was zero. So the investor is going to lose all the I minus A that they invested. And also the entrepreneur is going to lose their investment, A, the assets that the entrepreneur put in. And we'll assume actually that there's no more that the entrepreneur can lose. So only what was put in can be lost. And that's often called limited liability. So you're familiar with that phrase, I think. So limited liability is the assumption that the investor cannot claim more from the entrepreneur but what was already put in. So the question here is, can we design such a funding contract, or in other words, a choice of a distribution RB to the borrower, the entrepreneur, and RL to the lender, the investor, of the outcome when the project is successful, such that actually we make sure that the entrepreneur's objectives will be aligned with the investor's objectives. So now remember, this project is only going to be fundable or have positive NPV if the entrepreneur will provide the effort, puts in the high effort. So we need a funding contract or a division RB and RL that gives the entrepreneur an incentive to actually put in this effort. On the other hand, also for the investors, of course, there is a question. It must be worthwhile for the investor to actually invest their money. So RL, the part of the split that they get, must be enough to, well, make a profit, or at least not make a loss from this investment. Okay. So the question is that we need to solve. Can we find such an RB and RL that achieves these two objectives? So let's now go to the model. So it's on the slide actually, but what I'm going to do now is I'm going to do this again on paper, and then you can actually read this on the slides yourself. So I'm skipping now to the paper version. So there we are. So we have this investment I into the project, and the project might either be successful and provide payoff R, and that might happen, well, if there is effort, it will happen with this probability PH, right, the high probability. But if there is low effort or no effort, if the In other words, if the entrepreneur shirks, is lazy, then there will just be a lower probability of success, PL. And of course, there is this probability of failure here, and that's going to happen with 1 minus PH or 1 minus PL if the entrepreneur did not put in the effort. So this R, which is the outcome of the project, the amount of money that the project gives upon success, needs to be split in this part that goes to the borrower, the entrepreneur, and the part that goes to the lender, the investor, RL. And if there's failure, of course, there's a zero outcome and there's no splitting here. Now, if this entrepreneur didn't put in the effort, put in low effort, then there was, of course, also this private benefit, which is not observable to the investor. They know it's there, but they cannot see whether it was realized, which was B. So there might be a plus B to the entrepreneur, both if there is success and there is failure. Just the private benefits of being lazy, if you wish. So now let's look at these incentives for the entrepreneur. So I'm going to look at the entrepreneur or the borrower, if you wish. The entrepreneur. So if the entrepreneur chooses low effort, or let's call it no effort, the low part of this diagram, no effort, what does this entrepreneur get? In expectation, well, still, even with low effort, the project might be successful. So with probability PL, the probability of success with low effort, the entrepreneur will get his or her share, the RB that was agreed upon in this contract. And in addition, because this entrepreneur is not providing effort, they will get this plus B. So that's the payoff for the entrepreneur in case of no effort. On the other hand, if there is effort, the high effort case, then there's a bigger probability, a larger probability of success, going to be PH. PH times RB. That's what in expectation now this entrepreneur, this borrower is going to get out of this project if they do put in the effort. And of course, in that case, they don't get these private benefits because they put in the effort. Now we were wondering whether we could align those incentives, or can we make sure somehow that the contract is such that this entrepreneur is going to prefer putting in the effort. So what would that mean? The entrepreneur needs to be better off when putting in the effort than when not putting in effort. So we call this condition incentive compatibility. So this condition is called the incentive compatibility condition for the borrower. Is the contract, the division RB and RL, is that compatible with providing the incentives to put effort in the project? So what does this condition look like? Of course, the payoff for the entrepreneur, if they do provide the effort, if they choose to provide effort, the PH times RB should be bigger than what they get if they choose to be lazy, which was PL times RB plus these private benefits. So of course, if this is the case, then this entrepreneur is going to say, oh, I know that I might be lazy, but if I work, I actually get more. So I'm going to choose to work. Actually, we're going to make life a little bit easier for us and say, actually, we're not going to look strictly at a strict inequality, but we are going to allow actually these two values to be the same. So if they are exactly the same, you might argue, well, the entrepreneur is going to be indifferent between putting in the effort or not putting in the effort. And we're just going to assume that when the entrepreneur is indifferent, then they are also going to put in the effort. Doesn't matter for them anyway. Okay. So this is the incentive compatibility constraint for the borrower, for the entrepreneur. And we can rewrite this a bit into bringing this PLRB to the left-hand side. Write it like this: PH minus PL times RB should be bigger or equal to B. Or in other words, RB needs to be bigger than B over delta P. So RB needs to be big enough for this entrepreneur to be willing to provide the effort. One way of saying this is the entrepreneur needs to have skin in the game. They need to be rewarded for providing effort, because otherwise this B is going to sort of mess things up in terms of incentives. So the larger B, the higher actually the reward B needs to be for this entrepreneur to prefer indeed putting in the effort. Okay, so that's the entrepreneur side. Now let's look at this, the investor side. So as I just explained, the investor also needs to be happy, right? So what does it mean for the investor to be happy? The investor must be sure that, at least in expectation, they will get repaid what they put in. So the investor or the lender will only want to sort of participate in this project if they are so-called participation constraint is satisfied. So the participation constraint for the lender, what does it say? Well, in expectation, provided that the contract is incentive compatible, so that provided that the investor can expect that the entrepreneur is going to put in the effort. Well, what's then the outcome for the lenders is going to be an expectation PH times RL. And of course, this expected outcome needs to be at least as large for the investor to be repaid what they put in. What was that? I minus A, that was the amount, the investment cost minus the assets that the entrepreneur put in. That was what the investors provided. So the expected payoff for the investors needs to be at least as big as what they put in. Otherwise, it will be for them a negative payoff investment. By the way, I didn't emphasize this. I'm completely ignoring stuff like we have to discount. In real life, we have to discount, of course. We have a discount factor, perhaps not if the interest rate like now is almost zero, but in general, we would have this. We're just stripping that away from this model. It's not essential for this model. If you look at actual projects, of course, you want to be more careful. You might want to include that. But we want to sort of make a model which is as simple as possible to highlight basically the effects that we want to highlight. So we have to deal with that. So if we need to deal with that, we can sort of just plug that in later, and that's not a big addition. So we have a condition for the entrepreneurs, RB should be big enough. We also have a condition for the lenders, for the investor, RL should be big enough. But note that, of course, RB plus RL cannot be bigger than R, so it's actually equal to R. So we have to also face the fact that RB plus RL is going to be R. So the question boils down to, can we find an RB that's big enough and an RL that's big enough, but together they cannot be more than R? Is it possible to find such a split that satisfies both these inequalities? So let's see whether we can actually solve that problem. That's the question that we need to solve. So from our incentive compatibility condition for the borrower, so this one, we have just repeated here, RB should be bigger than or equal to B over delta P. Now since RB plus RL will equal R, so that And if RB should be bigger than or equal to B over delta P, the largest amount RL that we can promise to the lenders, so the maximum amount that we can promise to the lenders without violating this condition, this inequality, and the equality over here. So the maximum we can promise is R minus B over delta P. So if you promise more, then we cannot guarantee anymore this amount that's necessary for the borrower to put in the effort. So what that means is that, well, what we call technically the pledgeable income, you know, this with the letter P, a big P, capital P. Pledgeable just means what we can promise. It's jargon. It means what can we promise, what part of the income can we promise to outside investors in expectation at maximum. So the maximum payment that we can promise upon success was this thing over here, right? So in expectation, what we can promise, what we can pledge to the investors is, well, probability that we get is RL max. That's the maximum expected amount that we can promise to investors, and of course it reduces to PH times R minus B over delta P. Okay, so that's the pledgeable income, and we derive that from the incentive compatibility condition for the borrower and this fact that, you know, RB and RL can only add up to R and not more. So now we have to focus on this second constraint, the participation constraint. The participation constraint for the lender, for the investor. So what was it? Just repeat it. PH times RL, the expected payment that the investors get, should be at least as big as the amount of investment that they put in, I minus A. Well, if the maximum that we can promise, or the pledgeable income, is this amount, well, that means that, you know, whatever we put in here, it cannot be bigger than this amount. That's the maximum. So this is only going to have a chance of working, so it can work, only if this pledgeable income, or PH times R minus B over delta P, the maximum that we can promise, is going to be bigger than I minus A. If the maximum that we can promise is not sufficient to reward these lenders, well, then we can forget about finding a contract that both players will want to accept. Okay? So a different way of saying this actually is, so we can find an RB and an RL if, and only if actually, the assets A that the entrepreneur has to put into this project is big enough by rearranging this. So if you rearrange this, you'll see you can write this as A should be bigger than I minus PH R minus B over delta P. And just rewriting this a bit, PH times B over delta P, which is this part, minus PH times minus B over delta P, minus PH times R minus I. And this amount I'd like to call A bar. You can also find that in the book. We define this to be A bar. So what this says is we can only find this RB and RL provided that the amount of money that the investor has, that the entrepreneur has, the assets that the entrepreneur is going to put into the project, is bigger than some minimum value A bar. Well, how big is this minimum value A bar? This amount. It's something related to this B parameter, which is the attraction of shirking, of being lazy, private benefits. The larger the private benefits, the larger this lower bound A bar is going to be, minus the value actually of this project, because what you see here in these brackets is precisely the project NPV. Okay, so let's go back to the slide now. So all that I just did on paper is also actually in the slide. So we looked at this incentive compatibility constraint for the borrower, for the entrepreneur. Then we looked at the investor's participation constraint. What do they need in terms of RL, return from the project, to be satisfied, to be willing to invest into this project? And the question that we try to ask is, or to answer, is can we find payments, an RL and an RB, which add up to R, such that both this incentive compatibility and participation will be ensured? So we did some computations, and you can read them again or watch that part of the video again, where we introduced the maximum and in particular also the pledgeable income, so the expected income, the maximum expected income that we can promise to the lender. The pledgeable income was this amount, P, capital P. And from that, basically, we derived that there was a minimum bound to the amount of assets that the entrepreneur needs to put into this project to make this contract, this funding arrangement work. A should be bigger than this A bar, which is composed out of these two parts. So let's review what this result is. So the result is we had a participation constraint for the lenders. We combine this with the necessity of having incentive compatibility, so that the entrepreneur, we are sure that the entrepreneur is going to provide the effort. Otherwise, we don't want this project anyway. Nobody's going to be willing to invest in this. And that allowed us to derive some minimum amount of assets that the entrepreneur has to put into this, to invest into this project in order to make this work. This minimum amount was this thing that we call A bar. So in other words, there is some skin in the game in terms of money invested that needs to be there for this project to get flying, to get funding from outside investors. So if, therefore, this entrepreneur is poor in the sense that they don't have sufficient money themselves, sufficient assets themselves lower than this A bar, then there is no way that there's going to be any investment provided by the necessary outside investors, even though this project itself might have a positive NPV. So there's a positive NPV project, but because of this moral hazard bit, so the B part if you wish, the private benefits part, there is no way in which this positive net present value project is going to be financeable. On the other hand, if the entrepreneur does have enough assets, so A is bigger than A bar, then indeed investment is going to be provided. So the investor is going to invest then these I minus A, and they're going to figure out a way to basically divide up the R into some RL and some RB that both will satisfy those required inequalities, so those incentive compatibility constraints and participation constraint. There might be multiple solutions, or usually there are multiple solutions, basically multiple ways of splitting this up that all satisfy these two constraints. But we'll typically assume in most of the course, not always, and if we don't, I'll mention this, but we'll typically assume that there's just one entrepreneur and there's actually a lot of competing investors. And in this case, competition between investors is going to assure that the share that has to be promised to investors is going to be just low enough to just marginally satisfy their appetite for getting repaid. So we'll actually competition will actually drive down the additional rents that the investors might get to just sufficient to reward them for their investment. So PH times RL equals I minus A in equilibrium. What that means is that the entrepreneur in that case gets the rest, right? So the share that's going to be left for the entrepreneur is essentially R minus that RL, and it takes the form that you see here on the slide. So I invite you to check that. So just to summarize, what was our main question? The question was, from this model, can we design a financing scheme? So splitting up RB and RL of this total rewards upon success, such that the entrepreneur's objectives are aligned with the investor's objectives. And the answer that we found is, well, that's not always possible. It turns out to be only possible if the entrepreneur has sufficient assets of their own, if A is big enough. So this moral hazard, which is driving this result, actually results in what we call in finance credit rationing. Credit rationing to those entrepreneurs who have not sufficient money, so low net worth individuals, or if you want to look a bit further, low net worth firms. So these firms or these individual entrepreneurs in our model, they have a project which has a positive net present value, but still it's not possible to execute this project. They can get credit from outside investors to execute these positive NPV projects, and that's called credit rationing. So this moral hazard drives credit rationing. So what we'll do in the remainder basically of the course is look at possible solutions to this credit rationing. So we have a look at diversification, or carrying out some projects perhaps in sequential projects. That will be next lecture. We'll look at introducing a monitor who has perhaps a little bit more information on what the actions of the entrepreneur might be. And we'll have a look at some additional things apart from the cash flow rights that we just defined, the RB and the RL. There might also be alternative control rights or decision rights that will influence incentives. And those will be part of financial contracts as well, and they will sort of play a big role in the remainder of this course. So we will keep on sort of extending this particular model, this project model, this fixed investment model, to incorporate different stuff that we see actually in the real world, which will be put in there in order to ameliorate, to mitigate basically this credit rationing problem. So that's it for now. So I hope you will this video is useful, and perhaps you might want to sort of review a bit when you're sort of working on the tutorial questions. It will be posted on Nestor as well. And in the meantime, so while you're working on this, good luck. We'll see you in the tutorials either online or on campus. So online on Wednesdays and on campus on Friday. See you there. Bye-bye.